focus on how we can solve trig equations with using our identities. So please make sure you have your trig identity sheet handy, as we're going to refer to that back and forth. Let's take a quick look at something we would have typically solved in algebra. We would have had f of x is 2x squared plus x, and if they said to solve, we typically would tackle this by factoring. We notice that with our two terms, they both have an x in common, leaving us with 2x plus 1. We know that when we have two factors set equal to 0, to solve, we would set each factor equal to 0 and solve each one of them individually. So x would be 0 and negative 1/2. Since it's set equal to 0, this is the location in which we cross the x-axis. However, the same idea can be used when we're solving sine, cosine, tangent, secant, all of our trig functions. When I think about sine of x, where is that equal to 0? I know that x is equal to 0 when I look around my unit circle for sine at 0, pi, 2 pi, etc., 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 right? So let's use this same idea to combine what we did in algebra with what we're doing with trigonometry. I want to find all solutions between 0 equal to and less than 2 pi. Notice that 2 pi does not have a less than or equal to sign with it. It is just less than 2 pi. So be careful with what signs that we're using here. When I look at 2 sine squared of x plus sine of x equal to 0, you might agree that this looks quadratic. Notice on both sides, they both have a sign, so I'm going to factor out sine of x from both terms, leaving me with 2 times sine of x plus 1. So if I were then to distribute my sign, we would end up back where we started. Now that it's factored, we can set each factored piece equal to 0 and solve. I have sine of x is 0, and 2 times sine of x plus 1 equals to 0. I know that sine of x is equal to 0 by looking around my unit circle. The values that are between 0 inclusive and 2 pi are 0 and pi, because 2 pi is not included. When I look at my right-hand side, I can solve for sine by subtracting 1 and dividing by 2. Again, looking around my unit circle, I know that sine is equal to negative 1/2 when I'm at 7 pi over 6 and 11 pi over 6. Those are all within the parameters provided. My values then of x are 0 pi, 7 pi over 6, and 11 pi over 6. We can also verify this using graphing. Notice then I've put 2 sine squared of x plus sine of x, and it's set equal to 0, so we're looking for where is it crossing the x-axis between 0 and 2 pi not included. I now see 0, I see pi, I see 7 pi over 6, and I see 11 pi over 6. This next one that is on the far right-hand side would be greater than 2 pi, or equal to 2 pi. So we're not going to include that one because 2 pi is not included in our solution set. Let's head to slide 2 to see another example. Here I also have 3 secant squared of x minus 5 secant minus 2 equal to 0. My solution set is between 0, which is included, and 2 pi, which is not included. This does look quadratic in nature, but I'm going to use u substitution a little bit here to kind of break this down a little. I'm going to say 3 times u squared minus 5 times u minus 2 is 0, where u is equal to secant to help us out so that it's not so busy. I see I have a number in front of my first term, so I need to find two values that multiply to -6 and add to -5. -6 times 1 works. Because I have a number in front of u squared, I know I need to break apart my middle term. So I create 3u squared minus 6u plus u minus 2 equal to 0. There are many different factoring techniques. Perhaps you are more comfortable with guess and check. I utilize this AC split method. So feel free to use whatever factoring technique you are comfortable with from Algebra 2 and College Algebra to help with this. These are divisible by 3u. These are divisible by 1. 3u, u minus 2 plus 1 times u minus 2. This is perfect. We need our binomials to be equivalent. Factoring out our binomial, I have u minus 2 and 3u plus 1 equal to 0. Now that I have it factored, I will replace secant back in here. Secant minus 2 and 3 times secant plus 1 is 0. We can split these apart. I'll have secant minus 2 equal to 0, and then 3 secant plus 1 equal to 0. Solving on the left-hand side, we have secant is equal to 2. This is the same as 1 over cosine, which is equal to 2. Using reciprocal properties, this is also the same as cosine is equal to 1/2. I know that cosine is equal to 1/2 by looking around my unit circle at pi over 3 and 5 pi over 3. So we found two solutions. Noticing on my graph here that I've got pi over 3 and 5 pi over 3, but I haven't yet solved my second one. How come there's not more? Let's solve and see. This is the same as secant equal to subtract 1, divide by 3 to get secant by itself, or 1 over cosine is equal to -1/3. Using our reciprocal properties, this is the same as cosine is -3. Oh, but if I were to say the inverse of cosine, so I can find inverse of cosine of -3, so I can find what x is, that's not going to be possible. It's going to say undefined when you put that into our calculator. It's going to say undefined. Oops. It's going to say undefined because -3 is not in the range. So -3 is not in the range of -1 to 1. So it's going to come up as undefined if you try putting that into your calculator. Therefore, this one provides no solution for us, which is why we're only seeing pi over 3 and 5 pi over 3 when we're using the x-intercept, solving and finding the x-intercepts within our graph. Let's see in another example on slide 3. Here we have 2 times sine squared of x plus 3 times sine of x plus 1. Also between 0 and 2 pi, where 2 pi is not included in our solution. This also looks quadratic if we were to replace sine with u. So let's let u equal sine of x just to see this process again. So 2u squared plus 3u plus 1 equal to 0. I have a number in front of my u squared, so I need to use the AC split method. So what multiplies to 2 and adds to 3? 2 times 1 should work just fine. And then splitting our middle term. So 2u squared plus 2u plus 1u plus 1. Group in pairs of 2. The first two are divisible by 2u. The second is divisible by 1. 2u and u plus 1. Ooh, this is working out nicely. They have a common binomial. We will factor out the common binomial. And now that it's back into our factored form, we'll replace u back with sine. Sine of x plus 1 and 2 sine of x plus 1 equals 0. Setting both of them equal to 0, I'll have sine of x plus 1 is 0 and 2 sine of x plus 1 is 0. So I need to find where is sine on my unit circle equal to -1. There is one place on our unit circle where sine is equal to -1. That is when x is 3 pi over 2. I do see 3 pi over 2 as a solution when I'm graphing, finding the x-intercepts where it crosses the x-axis. I also need to find where is sine of x equal to -1/2 by subtracting 1 dividing by 2. There are two locations on my unit circle where this happens, at 7 pi over 6 and 11 pi over 6. 7 pi over 6 and 11 pi over 6. So we have found the three solutions to this particular one between 0 included and 2 pi, which is excluded. Let's see another example. They're going to get progressively a little bit more difficult as we go. In example 4, we have 2 sine squared of x minus cosine of x equal to 1. Still between 0 included and 2 pi, which is excluded in this situation. I've got sine and cosine happening here. What I'm going to do is replace this sine squared. I'm going to replace this using a Pythagorean identity. And I'm going to use the identity that has the cosine within that identity. So this is actually going to be 2 times 1 minus cosine squared of x minus cosine of x equal to 1. So I replaced sine squared of x with the Pythagorean identity 1 minus cosine squared of x. This works out nicely now that everything is the same trig piece, trig function itself. I'll distribute, so now we have 2 minus 2 times cosine squared of x minus cosine of x equal to 1. Well, if we're going to solve this, I need to set it equal to 0. So I'm going to rearrange my terms and combine like terms at the same time. This is the same as -2 times cosine squared of x minus cosine of x plus 1. If I had 2, subtract the 1 from over on the right-hand side, equal to 0. But I've got a negative out front. I'm not really a fan of that negative, so I'm going to divide everything by -1, so it turns my first term positive and also changes the sign of everything else. That'll just be helpful for us. Certainly utilize the u substitution that we've done in the previous examples. I am just going to jump to the factored form. I know I need to find two values that multiply to -2 but add to 1. Its factored form will be at 2 times cosine of x minus 1 and cosine of x plus 1 equal to 0. I'll let you factor on your own. I'll set each piece equal to 0, so 2 times cosine of x minus 1 is 0, and cosine of x plus 1 is 0. I need to find where is cosine of x equal to 1/2. Where is cosine of x equal to 1/2? Looking around my unit circle, there are two locations at pi over 3 and 5 pi over 3. Pi over 3 and 5 pi over 3. And where is cosine of x equal to -1? There is one location where cosine is equal to -1, and it is at pi itself. So here's pi itself. Notice when I put this into Desmos, I set it equal to 0 by bringing the 1 from the right-hand side and subtracting it so I can identify where are we crossing that x-axis. All right, slide 5, example 5. Slide 5, example 5. Let's try another example where we move and turn a sine squared utilizing cosine using a Pythagorean identity, still between 0 inclusive and 2 pi excluded. Using again that Pythagorean identity, I'm going to replace 2 times sine squared with 2 times 1 minus cosine squared equal to 3 times cosine of x. I now have 2 minus 2 times cosine squared of x equal to 3 times cosine of x. Bringing everything to one side and rearranging so it's in descending order, easier for factoring. -2 times cosine squared of x minus 3 times cosine of x if I bring it from the right side to the left side, plus 2 equals 0. Again, I've got that negative out front. Divide everything by a -1 to keep it consistent. And then factor. We need to find two values that multiply to -4, but yet add to 3. So your 4 times -1 would work. Split our middle term. I'll let you do that on the side. It's factored form. 2 times cosine of x minus 1 times cosine of x plus 2. Set each factored piece equal to 0. And cosine of x equals, jumping the gun here, plus 2 equals 0. Again, where is cosine on our unit circle equal to positive 1/2 when I add 1, divide by 2? Cosine is equal to positive 1/2 in two locations, pi over 3 and 5 pi over 3 on our unit circle. Also, where is cosine of x equal to -2 on our unit circle? Oh, again, this one is going to have no solution since -2 is not in our range. When we're looking for its inverse, it's not in the range, so it's not possible. Notice this time when I graphed, I set the left-hand side equal to 2 sine squared of x, and then I put another line for 3 times cosine of x. This is an alternative method that we learned in college algebra. The first one we looked at was where does our graph cross the x-axis? So when it's set equal to 0, where does it cross the x-axis? The other graph that we learned was the intersect method. Where does the left-hand side of the graph intersect with the right-hand side of our graph? And regardless if we do the x-intercept or the intersect method, we should get the same solutions. So notice where the red graph, 3 cosine of x, crosses the black graph of 2 sine squared of x is at pi over 3 and 5 pi over 3 as well. So another way in which we can find the solutions. Or you could have set the equation as 2 sine squared of x minus 3 cosine of x and set it equal to 0 and found where it crossed the x-axis. Let's try another example. Try another example on slide 6. Here we have tangent is equal to 3 sine of x for all solutions between 0 and 2 pi. Here, I'm going to replace tangent with sines and cosines. When we were working with trig functions earlier, we also did this. I'm then going to get rid of my fraction by multiplying both sides by cosine. This also then provides us with sine of x equal to 3 sine of x times cosine of x, where I'm going to bring this 3 sine of x cosine of x to the left-hand side. 3 sine of x minus 3 sine of x cosine of x, setting it equal to 0. You'll notice that they both have a sign in both of our terms. They both have signs, so we're able to factor out sine of x, leaving us with 1 minus 3 cosine of x equal to 0. And now that it's factored, we can set each factored piece equal to 0. Where is sine of x equal to 0 between 0 and 2 pi? Well, that would be 0 and pi. Where is cosine of x equal to positive 1/3? When I subtract 1, divide by negative 3, positive 1/3 is not on our unit circle. We need to use inverse functions using the definition. Make sure that we're in radians on your calculator because we are in radians within our description here. When I put this into our calculator, we'll have 1.232 radians. But we do know that there's also going to be a second solution because cosine is also positive in the fourth quadrant. So right now we have 1.232 radians from here to here. But I also know that cosine is positive in my fourth quadrant. So what is the value in radians from here all the way around to here? Well, I can find that by taking 2 pi minus 1.232, and I'll get approximately 5.052. So we've got four solutions, some nice neat pi radians and some other decimal versions. I also used the intersect method here, where I set tangent equal to one line, which was the left, and 3 sine of x, which was equal to the right, and found where they intersected each other at 0, at 1.231 or 232, depending upon how you're rounding, at pi, and down here at 5.052. Yes, there is another intersection here, but 2 pi is not included. 2 pi is not included, so we're stopping where we're at. Let's head to example 7. Example 7 uses secant equal to 2 times cosine. Well, again, secant we can turn into a cosine, and therefore all of them are in cosine, which is easier for us to find on our unit circle. So let's start there. Let's turn secant into 1 over cosine equal to 2 times cosine of theta. I'll multiply to get rid of my fraction. I now have 1 minus 2 cosine, 1 equals 2 cosine squared of theta. I can divide by 2, so 1 over 2 is equal to cosine squared of theta. And then take the square root of both sides. I'll have plus or minus is cosine of theta. This gives us plus or minus 1 over the square root of 2. However, in order to find the solutions on our unit circle, we have them written where our denominator is rationalized. Rationalizing the denominator will provide us with square root 2 over 2. So where on our unit circle is cosine equal to plus or minus square root of 2? There are 4 locations, one in each quadrant. We have pi over 4, 7 pi over 4 for the positives, 3 pi over 4, and 5 pi over 4 for our negative values. I also used the intersect method, substituting exactly what I saw in our equation, the left side, the right side. Where do they intersect? Pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. Or you could set it equal to 0 and find the 4 locations where it crosses the x-axis. Our last example. Here I'm starting out with 4 over secant squared plus 3 cosine equals to 2 cotangent times tangent. All kinds of weird things. Again, turning into sines and cosines first. I'm also going to turn cotangent into tangent because we're going to see what happens. Secant allows me to rewrite this by moving secant up to the top so that I have 4 times cosine squared of theta plus 3 times cosine of theta. Well, cotangent is the same as 1 over tangent. So they're kind of tricking us here. Times tangent. Common factors can eliminate, all gone. So the only thing that's left on the right-hand side is 2. I'm going to bring that to the left-hand side so that all of our pieces are together so that I might be able to factor. However, there is nothing that I can think of that will multiply to negative 8, but yet add to 3. Nothing that will work. That means we need to use Pythagorean theorems. We need to use the quadratic formula. So cosine of theta equals the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times our a value. Simplifying this gives us negative 3 plus or minus the square root of 41 over 8. That gives us 2 results, right? Negative 3 plus the square root over 8 will end up with 0.425. And when we take negative 3 minus the square root of 41 over 8, we have negative 1.175. Notice this is not in the range of negative 1 to 1, so this solution will not work. We have one option. We have cosine of theta equals 0.425. I can find what theta is by taking the inverse of this value using our definition to find theta, which is 1.131. If you were to do that and if you didn't see that this negative right off the bat wasn't going to work and you plugged that in here in our calculator, it would say undefined. So that would be your indication that that's not a good solution. So if you don't remember that off the bat, that's quite all right. But we know when I'm thinking about where 1.131 is somewhere over here, this is 1.131. Cosine is also positive in our 4th quadrant. So what is this radian value? What is this radian value? which can be found by taking 2 pi minus 1.131, or approximately 5.152. So there's two solutions. I did the intersect method, putting it in exactly as I said. See the left side, where is that equal to the right side? We know that 2 cotangent times tangent ended up with just 2, so it shouldn't surprise us that we end up with a horizontal line. But we do see that they intersect at these 2 locations together. So please utilize Desmos to help us graph so that what we're finding algebraically matches what we're finding graphically as a way to help verify what we're seeing happens together.